task is actually, there's a lot of advanced software being used in these tasks. However, they still require like a human to actually go through it and maybe label things properly so that, you know, the machine isn't to blame alone, all right? However, this is definitely a task where AI can improve it, because humans are definitely prone to error. And there are a number of applications, mainly in the MRI domain, that are being done better by convolutional neural nets and advanced neural nets. So as I said, there's a huge initiative to use computer vision and deep learning to automate many of these tasks. So there's a lot of tasks that can be improved with computer vision, not just robotic surgery, which is actually going to be a main application in the future for computer vision. However, right now, the trend seems to be in a lot of these medical scans, things like CAT scans, X-rays, ultrasounds, PET scans, and NMRs. And there's so many different types of diseases to look for it. This is an ideal area for startups to take advantage of. And the use cases for this are endless, from cancer detection, disease monitoring, Alzheimer's, and many, many other ailments. So computer vision can definitely revolutionize the medical industry and improve patient care and get much faster diagnostics and even be used to find cures much faster. Okay, so let's talk about UNet. UNet is a CNN that can actually do image segmentation. So let's see how it works. UNet was created in 2015, and it basically was a CNN specifically developed for the biomedical image segmentation task, which is what we're going to use it for in our project at the end of this chapter. UNet has now become very popular for end-to-end encoder-decoder type networks for semantic segmentation, and it has a very unique architecture. It's called an up-down architecture, which has a contracting part and an expansive part. And you'll see it in the diagram here, where you can see this is how it starts. The input image comes in, and basically it goes down this contracting part here, and then there's this middle area here that's called the, well, that leads, sorry, to the expansive part, okay? And basically the output here. So first things first, take a look at this. We have an input image here, and it's outputting an image, or basically a segmentation map. That's effectively an image, because we're going to use it to segment the other image. So basically there's another label here of the contracting part and the expansive part. So, oh yes, the area I wanted to talk to you about was the bottlenecking area here, okay? So this is how UNet structure works. There's a downsample, a bottleneck, and then an upsample. The downsampling part in UNet consists of 4 blocks. There's these 3x3 convolutional layers with all these ReLU, batch normalization, and dropout used. And this is basically 4 layers here. So there's these 2 conv layers here, 2x2 max pooling, and then the feature maps double as we go down, which is not unusual. We've seen it happen in VGG as well. And starting at 64 and then going to 128, 256, and 512. If you go back to the diagram, you can see it here, 64, 128, 256, and 512. Then it's bottlenecked here, and then we basically do some downsampling again, going back here to get the output segmentation map. So the bottleneck, let's talk a bit about this. This consists of 2 convolutional layers with, again, batch normalization and dropout, okay? Nothing majorly special here, it's just how it works. It doesn't follow a traditional CNN architecture where there's a continuous growing. There's this continuous growing here, and then is this bottleneck, and there's this downsampling here. So the upsampling part. Now the upsampling part basically consists of a similar pattern. However, instead of a convolutional layer, there's this something called a deconvolution layer. And then it's concatenated with the feature map of the corresponding contracting part. This is basically the major area here that allows UNet to work. And basically then it has 2 conv layers here to create the output up here. And if you're wondering what a deconvolution layer is, because I mentioned it in this preceding slide, basically it basically reverses the effects of a convolutional layer. So just imagine what a convolution layer does. A convolution layer basically applies some transform to the image. Well, a deconvolution layer does the same, however, basically the opposite. So it produces basically the output of a reverse convolutional layer. Hopefully that makes sense to you. What we're going to do now is going to define some more metrics you need to consider when making an image segmentation CNN. Okay, so that brings us to chapter. Okay, so welcome to chapter 19.3, where we talk about the intersection over union. Now, that may not sound... Hi, and welcome to chapter 19.3, where we now talk about intersection over union metric, which is an important metric you need to know when we're actually training image segmentation CNN. So let's talk about this first, okay? So let's assume we're doing some object detection here. And basically the green box here is our true bounding box over this nice car. So this is like a human labeled image of what it is. And now our classifier or predictor gave us this bounding box here, this red one. So generally it's correct. I wouldn't say it's wrong at all. However, you do see that it could have been brought in a lot closer here and maybe brought in a bit lower here and a bit lower here. So it's a good box, but not the best box. So how much of the correct area is covered by our predicted bounded box? That is this area here. So honestly, it seems like about 90% of our true box is covered by our predicted box. So how do we measure this in a metric? Okay, what is a good metric for this? What if this was a bounding box here? It still covers 90% of our true box. However, this is a much poorer bounding box than this one. This is where the intersection over union comes in. So IOU, I'm going to call it that for short, is basically the size of the union, that's the shaded area here, over the size of our predicted box. So you can see the size of our predicted box here is much bigger than the size of this predicted box. So what does that mean? It means that the IOU with this box is going to be maybe like 0.5 compared to the IOU of this box, which is going to be probably like 0.9. So generally though, typically an IOU over 0.5 is considered acceptable, mainly because object detection is very hard to get right. So we do have a fairly lenient threshold. And obviously the higher the IOU, the better the prediction. And essentially IOU is a measure of overlap, or how good basically the overlap is. So before I begin to show you how we actually implement IOU in Keras and use it as one of our metrics we monitor during training, I'll tell you why we need this for image segmentation. Remember, in image segmentation, we're basically measuring overlap of like our masked image over the original image. So suppose we're developing a mask that covers this image with just a car here. Forget about the bounding box for now. We just want to measure this mask here. And what if so imagine we have a mask, pure yellow mask covering this car. And imagine we have a predicted mask, that is our segmentation algorithm, that produces something that covers a blob like this here. How do we measure the effectiveness or basically the accuracy of this mask, given that this was the correct mask here for this image? That is why we need IOU still. IOU is not just used for object detection, it's used for image masking, which is segmentation. So now let's see how we do this in Keras. It's pretty easy to define these custom metric functions in Keras. You just have to write a simple function that basically takes in your true labels versus your predicted labels. We compute an IOU score, and these labels here aren't just going to be labels, they're actually going to be masks. And what we do here, when we compile our model, we define our own metrics. Previously we used to use accuracy. Now we just use my own IOU metric, which is going to be this function here. Alright, and then we train, and when we're training, we actually see the report here. So we see that my own IOU metric, which is this function here, technically there should be the same name here, just remember that. I should have done that for you guys so you don't get confused. But it's actually going to output the score. So instead of monitoring a loss in accuracy, we're now monitoring a loss and our custom function. So that's pretty cool. So let's move on to the next chapter. Hi, and welcome back to chapter 19.4, where we're going to implement this project, and the project is called Finding the Nuclei in Divergent Images. So let's go on to see a bit about it. So this was part of Hagel's Data Science Bowl of 2018. Basically the challenge was to spot the nuclei to get speed up cures. That was the tagline used. And what we wanted to do, or what they wanted to do, was automate nucleus detection. So we basically you'll see the images soon, but basically perform nuclei detection in these images. And this is basically the write-up they used here. Identifying the cell's nuclei is a starting point for most analysis, because most of the human body's 30 trillion, wow, that's a lot, cells contain a nucleus full of DNA, the genetic code that programs each cell. So identifying the nuclei allows researchers to identify each individual cell in a sample And by measuring how many cells or how cells react to various treatments, the researchers can now understand the underlying biological processes at work. So you can see this project actually has tremendous application in the medical field. And this was the flyer, as well as the tagline I mentioned to you before, that Kaggle used to advertise this contest. So you can see there's definitely a need, a practical need, to get this done right. So these were the images in our data set here. Look at the first row here, these 4 images. We were given images like this. These dots represent nuclei, and is basically different shades of gray, like these were all in the test data set. We actually have full color images here, as well as some basic grayscale images here. So these definitely seem like they could be, you can use some OpenCV thresholding functions and get these masks. These were the human labeled masks here. However, when it comes to these here, you definitely need some sort of intelligence to actually extract this and label nuclei here. As you can see, doing this manually as a human is going to take some time, definitely. And then getting the counts of over countless images is going to be an exhaustive task. So the first, this was the row of the true, well, the original images, the true mass, and again, more true images and more true mass. So we're going to train a classifier to take this image input, or this image, any image here, and produce a mask that looks like this. So our approach is basically to use UNet. It is a special CNN designed exactly for image segmentation tasks like this. So let's get started. Okay, so we're back to our virtual machine, and we're going to use UNet now in our medical imaging segmentation project, which is finding the nuclei in divergent images. Okay, so firstly, I want to make sure you downloaded the dataset correctly, and I want to actually show you something in this dataset. It is different to the type of datasets we used before, because now it has mass. So let's open this dataset here. So hopefully you've extracted it here. And as you can see, yes, it has the same train and validation folders, but look at this. It's no longer images now, it's actually folders. So what's in this folder? We have an image here. This is our test image, which we are supposed to produce a mask from. And now what is this? We have a folder of mask, and these are multiple files. And if you look at this, there are multiple images. Each one is a nuclei label. So what we're looking at, if we go back to our presentation here, let's bring this up. Actually, you can leave it like this. What we're looking at right now is basically this mask here is basically all the images we just saw. Let's minimize this, stacked upon each other. So the data is not as easy to basically not interpret, but actually use as we would for all previous tasks. We do have to do some processing on this data. So that's our data set here. So now let's go to our IPython notebook. I already have it loaded up here. So this code here is basically code that was provided by this guy here. He actually made the most popular kernel on Kaggle, top rated one for this project. And there were a number of contestants. And this guy had probably the best example of how it works. So let's run his code, okay? So we have the images here, 128 size he defined. We have our folders pointing to there. So we run that and fine, imports everything successfully. Then we set our training paths and our test paths. And this is the part that is very important. Remember I showed you how the nuclei are basically on one image at a time. So basically one input image has a bunch of sub-images that each one having one nuclei labeled on it. So what he does here, or what we do here, is that we basically stack those images together. So effectively, you can read the comments and stuff I've left in here. What we do is we basically take these images here and combine them into one single image with all these nuclei in that image, because that's basically the final mask we want to produce. So we have to process our training data a bit. So I'm not going to run it because it takes some time. I've already run it successfully here, and you can do so yourself. In fact, you will have to do these things yourself because it's run on my machine, it's not run on yours. These are like basically statements that save, but they don't actually store any of the data in this notebook, just the outputs. So let's do some illustrations here. He has some nice code here that generates this plot, and in this plot we can see This is image 0 here, and this is our concatenated or stacked mask that we produce from our input data. And he does it for quite a few images here, so we can actually see there's a lot of variety in the input images here. There's these grayscale ones like this, seem to be the most popular. Then there's these color images here. Then there's these here. These look like something from a microscope slide. And then there's these here that look a little different. Then there's this type here. Hope you can see what I'm pointing at here. So there's a lot of different types of images here. It's not one simple standard data set. It's a bunch of different types of data, all looking at nuclei though, and all having masks that output like this. Or labeled like this, I should say. So this is a function we used before. It's not actually one we're going to use. This was the example one I used in my slide. So I'm taking it off and deleting this empty cell. So this is the actual IOU metric here that he's going to use, or we're going to use in our project. I'm not going to go through the detail of how it's calculated, but it is very similar to the calculation we saw in our slides, just it's a bit different for mass. Alternatively, there were a lot of discussions on the Kaggle message board about if this IOU function was the best metric to use. So here's an alternative one you can use. Feel free to use it, and this one uses this one inside of it here. Okay? So, and actually I left another one here too. This one actually, there was basically a consensus that this was the best IOU function. And you can see it's quite exhaustive, pretty technical. Someone did spend a lot of time making this function. So this is the important part here. This is, well, this was equally important, this IOU function, but this is the core of what I wanted to show you. This is how we build our unit model. So two things to note, okay? You're seeing we're actually basically assigning a model layer. Instead of doing model.add, we're assigning layers to variables here, and then we have this S in brackets here. So what exactly are we doing here now? Well, this is simply another way we can build models in Keras. Keras is quite flexible. So what we're doing here, we're connecting models by having it here. So instead of using model.add, we're connecting them here. And there's a reason we can't use model.add. It's because of how the unit structure is, which is basically like a bottleneck at the bottom and deconvolutions going up. It's not easy, or it doesn't facilitate the model.add method in building this model. We sort of have to do it like this now. So we can see C1 is defined here, connected to this lambda function, which basically normalizes the inputs. Then we have C1 here and C1 here. So what this does, it basically tells this is our convolutional layer here with dropout that's tied to C1. And this is another convolution here tied to C1 again. So this is linking all of these layers together. And then we have max pooling here that basically it's called P1, this connection. So now this is linked back to these here. So we keep going forward. As you can see, the kernel or filter sizes get larger and larger as we go down. And then we do this here. This is how we concatenate our basically bottleneck or bottlenecking point here. And basically now we just go up, the up of the unit. Unit is called a U mainly because it looks like a U in those diagrams. And we're using a different type of convolution here, conv to the transpose. That's basically how we do the deconvolution layers here. So it's going up, and then we have our outputs here. So there's something I want you to note as well. Look at our output of the deconv. It's basically a grayscale image, 128 by 128 with one dimension. These are a number of parameters, not that much, definitely trainable on the CPU. So now let's fit our model. So we just do our basic callbacks here, and then we just fit our model here. This probably should just not be here, not sure what I was trying. And here we go. So you can see, I'm not going to run this now, but I've run it before, and it doesn't take that long. We're training it here. It's quick, just over a minute per epoch, which is quite quick. And we can see our metric loss here, my IOU metric. So let's see what function is that. Let's just go up. That was this one here. That was the big one we used. This was the one I actually remembered in the Kaggle discussions that was the best IOU, or the most appropriate IOU. Not saying that these were wrong or these were bad. It's just that this one was actually the most relevant to segmentation tests. Segmentation IU is very different to object detection IUs, which use boxes. So we needed to develop something custom. This was definitely a big part of the Kaggle challenge in this project. It wasn't just applying unit to data. It was coming up with a way to actually assess the performance of this model. So we can see our IU metric changing as it goes, and our validation IU metric going up. So we want this to go up actually. So we want this to get better over time. So after 10 epochs, it wasn't great, 0.46. In terms of accuracy, that is not a good metric. However, this is not accuracy. This is an IU metric, and IU metrics don't really correlate exactly to what accuracy means. So 0.46 is actually a pretty good value. I've seen on Kaggle some guys got up to 0.77 or 7 or 0.8 using this metric after training on some GPUs from multiple epochs and tweaking a lot of the other training parameters above here. But for now, 0.46 is actually pretty good. And you may have noticed actually the code just changed here, and that was because I actually had some confusion here where I was experimenting with different IU metrics, and I confused myself because when you load a model, or when you create a model, it is specific to this metric here. So when you load a model, you actually have to specify what metric you used when training the model. So we just trained using my IU metric, which was the function, if I scroll all the way up, defined right here. This IU metric basically used all of these functions here to basically calculate it. This was the best one according to those guys on Kaggle, which was the most representative of what our loss should be. Okay, so now what I'm going to do, we basically we load our model that we just trained, or you can just use model if you're training it within the notebook. You don't have to load it. Okay, and basically we just split this up, the data, our X train data, into 90% basically being our training data and the last 10% being the validation data, and we just create our mask from this now. So now let's take a look and see how our mask look. Okay, so if we just run this function, you will see this was the training image here. This was the mask that we concatenated previously from these here. And then this is the predicted mask. As you can see, it is very, very similar to this mask. There are some slight differences at a pixel level. However, this is actually quite good. And now we can do it on some of the validation data. So this was the actual input image here, and this was the predicted mask out of it. So as you can see, this is actually doing a pretty good job at image segmentation. And it only took maybe about 15 minutes to train on a CPU system. So feel free to experiment with this. You can create your own mask. Not sure if you know how. What you can do is probably get some software. I'll probably put a link to some software in the resources here where you can start annotating and basically creating masks from images like this. So if you want to try some medical imaging segmentation tasks or any other sort of segmentation tasks, you will know exactly how to do it. Okay, so welcome to chapter 20, where we finally get into object detection. And basically this chapter is split up into 4 sections. First is where I introduce the concept and basically how object detection all started and what it evolved to. And then in 20.2, I start talking about more modern day CNN based object detectors. So we go from RCNNs to mass CNNs. And then I take a look at single shot detectors, SSDs, which are one of the most modern object detector algorithms out there. And then I discuss YOLO, which is a competing object detection algorithm right now. So these two are the latest and greatest state-of-the-art object detectors, and we're going to test them. We're going to go through them in detail and then test them in the following chapters. Okay, so let's start at the beginning. Let's talk about early object detectors. So I'm going to introduce you to the history of it. So firstly, object detection is one of the holy grails of computer vision. Because previously, what we have been doing is just classifying like an entire image and saying what object or what class it belonged to. But can we take an image like this and label each major component being a dog, car, person, horse, another person in the back? Not yet, until we have come across object detection. So object detection is a mix of object classification and localization. Object detection is the identification of a bounding box outlining the object. So like in my face here, basically it's extraction, a bounding box around my face. And face detection is perhaps one of the most popular object detection algorithms that we all know and we're all quite familiar with from using cameras and our cell phones. Okay, so basically it tells you, instead of telling you this object here is a cat, it actually tells you where is the cat, and that is the whole point of object detection. So let's get into the history a bit, and let's start with Haar cascade classifiers. Now there were many object detectors before this. However, Haar cascade classifiers is what made it mainstream and quite popular because it was so fast. So basically this was developed by Viola Jones in their face detection algorithm in 2001, not that long ago, 17 years ago to be fair. And it was super fast, and it's actually still used today in a number of applications. Basically it's been optimized and tweaked to be even faster, so it basically reduces the CPU load, and it's very, very accurate. Basically what it does, it's a cascade of classifiers. That's basically how it got its name. And it uses Haar, basically. Let's go on to the next slide. Actually, I don't have it in this section, but it basically uses Haar features, and Haar features are basically like you have rectangles overlaying here. Like imagine a white rectangle here and one here, and then there are different types of Haar cascade classifiers. So basically it's just a feature extraction, basically what we learned before, and it's slid, this box here is slid over the window, over and over, continuously looking for a face. They're very good, but they are pretty hard to train and develop and optimize. So let's move on to histogram of gradients in SVM sliding windows. So sliding windows is a method where we extract segments of our image piece by piece in the form of a rectangle extractor box. So I mentioned it in the previous slide when I was talking about this box being slid across this image. What it does here in this image, this is a picture of my wife from her last bodybuilding bikini competition 2 months ago. And what it does here is just imagine this window is being moved here, then down here, and then down here. Just like, remember how we moved the kernel across the image in CNNs? It's exactly the same thing. And we can actually set the same parameters like stride and the size of this box. And what this box does here in sliding windows with histogram of gradients in SVM is that it basically extracts the HOD hogs or histogram of gradients in this box at different scales. So basically it does it with the image at one scale, and then another scale, a smaller scale, and then this one here. And this one basically has no room to go right, it just goes straight down. And it tries to match up the hog gradients with what it knows it's supposed to look like to find the object. Now, as you can see, this could be an effective way, but it's not really that resilient. Why? Because imagine we have to do this for every segment of the image continuously. It gets exhaustive and computationally expensive. So previous object detection methods are basically just feature extraction. I just mentioned that. And why would we want to actually manually find out features if CNNs can actually eliminate that? All right, CNNs actually automatically find features by just running all this training data through the algorithm and finding the loss, matching it with the correct class. So that's what's brilliant about CNNs. It takes that step away from us. So as I said, one of the problems with doing this is that it's issue of scale. Imagine this is a simple image that's 20 by 20. So this box can be passed over here. But imagine if this was a much bigger, like a 1080p image. How many different boxes would we extract? How do we know what size the box should be? I mean, that's when we rescale the image, but how many different rescalings are we going to do? So as you can see, this is not a very effective way of doing object detection. So I talk a bit about histogram of gradients. I'm not going to go into this in detail. I've taught this in my other OpenCV course. The videos are included free in that section, so that's why I'm not going to talk about it much here. But basically the slides are here for you to go through on your own, and you can pretty much infer from these steps here what hogs really are. So now we move on to RCNNs. Okay, so welcome to 20.2, where we talk about all different types of RCNNs, going from typical original RCNN all the way to faster RCNN and mask RCNN. So let's see what this is about. So what does the R in RCNN stand for? It stands for regions, actually, not recurrent. That's a different type of neural net. And this RCNNs were first introduced relatively recently in 2014 by researchers at the University of College of Berkeley in California. And basically they dramatically improved the performance on the Pascal VOC challenge. This is the equivalent of ImageNet for object detection testing. Okay, it's an example of some of the images in that dataset. So RCNNs attempted to solve the exhaustive search previously performed by sliding windows by proposing bounding boxes and passing these extracted bounding boxes to the image classifier. So how do we find these bounding boxes? Like, how are they proposed? They're proposed by using the selective search algorithm. And this is like a simple illustration of what happens here. So we have an image here, we have the proposed bounding boxes, and then we basically use these boxes, pass it through a CNN, and try to identify what is in it. So let's talk about the selective search algorithm. Selective search attempts to segment the image into groups by combining similar areas such as colors, textures, and propose these regions as interesting bounding boxes. So we have this image of some sheep here, and what selective search is going to do is going to try to like merge different similar pixels, similar lighting conditions, that sort of stuff, so we can kind of eventually get something like this. And then it's going to draw a box over each segmented region and propose that. Now there's a lot more tweaking we can do in selective search, so it all depends. Basically we can get little boxes or a lot of boxes. So when selective search has identified these regions of boxes, it passes this extracted image to our CNN. Example, one trained on ImageNet. Okay, that would be a very good CNN to use. We don't use a CNN directly for classification though, although we can. We use an SVM to first classify the CNN extracted features. Now, I didn't mention that before, but what happens here is that instead of actually passing the CNN here, using the CNN to get the classes, what it does, it just gives you the CNN features, which are basically the feature maps, all right? And then we use an SVM to classify the CNN extracted features. This was probably done for speed, because if I'm not mistaken, RCNN was the original proposed object detection, and it was meant for video. So speed was a concern. So after the first region proposal has been classified, we then use a simple linear regression to generate a tighter bounding box. That's how the boxes were actually basically sized and fit around the objects in the image. But how do we know what a good box is though? And that's where we come up with our IOU metric that we discussed before. Remember IOU? Basically it measured how good the overlap of the predicted box was over the labeled box. Now here's a problem that happens in RCNNs and basically all object detection algorithms. They don't often just propose one box. They propose many boxes over the same image sometimes. So remember in IOU 0.5 was considered a good result? Well, what if we have multiple boxes and they're all given over 0.5? This is a common problem, okay? So in the figure below, let's go through this example. We have 4 boxes in red. These are them right here. The green is the true box, the true positive. And as such, we have 1 true positive and 3 false positives, okay? So the 3 false positives here would be these boxes here, 1, 2, and 3, okay? So the reason it's 3 false positives is because we have 1 box here, the dotted line right now. This is basically our best box, so that will count as a true positive in our predictions, all right? So for now, just ignore the green box. He doesn't count in this calculation. We just have 1 box that's really good. He's our true positive, and 3 that aren't good. They're false positives. So mean average precision. It is a very tricky metric, in my opinion, mainly because it's not that intuitive to understand. I have the formulas fit here. What I'm going to say though is I'm going to try to explain it to you without going through this math. I've left a math for you in the slides so you can go over on your own and try to make sense of it. There's also a couple of blogs that have some very good but pretty lengthy explanations for it. But let's go back to this, sorry. So what I'm going to say is that actually in this blog here is a very good explanation for it. But essentially what mean average precision tries to do is that it knows all the boxes the object detector proposes. And basically what it tries to do is try to come up with a metric that defines basically what is, like let's say object detector A predicted this, but object detector B predicted maybe 4 false positives and maybe like some other boxes that were probably irrelevant and stuff. So, and then we remember this is just for one class. Remember there are different classes as well. So mean average precision is a way to measure how effective all of my object detectors were actually were. Okay. So just remember this is the metric of how we baseline and how we measure performance of object detectors. So now let's move on to non-maximum suppression, and this is a technique that object detectors use to remove overlapping boxes and thus improve their map scores significantly. So what this does, basically, it looks at the probabilities associated with each box that's being generated, and the probabilities it looks at are the probabilities of the object being in the same class effectively. So if we have like 2 or 3 boxes that say this is a car, but they have high overlap, what it does now, it looks at the highest probability box. That's this one here in red. And what it does, it checks the IOU with the other boxes. So in this image here, we see that we have 3 boxes here that our object detector has basically highlighted. And these are the probabilities of it being a class. So what it does, it checks the IOU over these here. And what it does, it will drop the boxes that it deems basically not as relevant as the main box. So that's effectively how we clean up these boxes that the IOU, that the object detectors produce. So now let's move on to fast RCNNs. This was announced or released in 2015, the year after the original RCNNs came out. And basically what happened was that the problem with RCNNs was that it was effective, but pretty slow, as each proposed bounding box has to be classified by our CNN, and as such, doing that in real time was far from possible. So it required 3 models, and it also required 3 models to be trained separately. So we had to have a feature extraction CNN, an SVM to predict the class, and a linear regression model to tighten the bounding boxes. You remember all these things we discussed earlier. So this definitely is a bit of a lot of moving parts in RCNNs. So what did faster RCNNs do? Faster RCNNs firstly reduce the number of proposed boxes by removing the overlap generated. So how did it do this? We run the CNN across the image just once instead of many times using a technique called region of interest pooling, or ROI pool. Okay, so ROI pool allows us to share the forward pass of the CNN for the image across its subregions. This works because previously regions are simply extracted from the CNN feature map and then pooled, which therefore you only need to run the CNN once per image and basically use that output of the CNN going forward. So combining the training of the CNN classifier and the bounding box regressor into a single model, that's what it did. So we have the SVM feature classifier, and that now became a softmax layer on top of the CNN. And our linear regression, that was tightening the boxes, basically that became a bounding box output layer parallel to our softmax layer. So basically what it became is this. So we have our feature extractor CNN, we have our softmax layers at the end of the CNN being our classifier for the object type or class, and then we have this in parallel, a bounding box regressor. So that is how fast RCNNs solve a lot of the delays and sluggishness of the original RCNN. So now a year later, in 2016, faster RCNNs made their release, I should say. So faster RCNNs made significant speed increases. However, region proposal still remained relatively slow, as it still relied on the selective search algorithm. Fortunately, a Microsoft research team figured out how to eliminate this bottleneck. So how did they speed up region proposal? Selective search relies on features extracted from the image. What if we just reuse those features to do region proposal instead? Okay, so that was the insight that made faster RCNNs extremely efficient. So you can take a look at the diagram from the paper here. So basically this line here is what is important. What if we reused those features to do region proposal? That is exactly why we don't have to keep running this over and over. Well, not over and over, but using selective search to generate our proposals. So how do we do region proposals with faster RCNNs? So faster RCNNs add a fully convolutional network on top of the features of the CNN to create a region proposal network. That's what we're seeing here. So there's now, let's go back to it. There's now a fully convolutional network on top of the features of the CNN. So let's think about that. So we have a CNN that produces this here, and there's a fully convolutional network here that does this region proposal. Okay, so the authors of the paper state the region proposal network slides a window over the features of the CNN. At each window location, the network outputs a score and a bounding box per anchor, hence 4,000 box coordinates, where k is number of anchors. That is basically how it works. I encourage you to read the paper if you want to get into more detail about faster RCNNs. Anyway, so back to this. So after each pass of the sliding window, it outputs k potential bounding boxes and a score of confidence of how good this box is expected to be. That's pretty cool and pretty complicated as well. So producing the bounding boxes now. So previously we mentioned we produced k potential bounding boxes. These bounding box proposals are proposals of common or expected boxes of certain shapes, aspect ratios, and sizes. These aspect ratios are called anchor boxes. So what's happening here is that our boxes, the boxes we propose in this method are basically predefined, and they're basically of certain shapes, ratios, and sizes. So the region network proposal outputs a bounding box per anchor and a score of how likely the image in the box will be an object. So now let's move on to mask RCNNs, which is pixel level segmentation. Now, mask RCNNs aim to combine object detection and classification with segmentation. As we previously saw, segmentation is the labeling of objects per pixel level, as we can see in the above image. So how do mask RCNNs work? They're basically an extension of faster RCNNs, where a binary mask is created for the object in the detected bounding box. So you remember how UNet actually created a mask that was basically provided our segmentation outputs? That's what's happening here in faster RCNNs. So a binary mask, basically a 0 or 1, is created for the object in the box. So we're now looking at a box here, and we're creating a binary mask for each box that's found. And this is the architecture of the network, and a link to the actual research paper where this publication was really released or made. So mask CNNs use something called ROI align. So the mask output uses the CNN extracted features to create its binary mask. So how did the authors of this paper achieve this? They used ROI align instead of ROI pool, as ROI pool's feature map was misaligned from the regions of the original image. That was something I read in the paper, and I was a little confused to why, but they explained it pretty well. So mapping a region of interest onto a feature map. So imagine this was the original input image here, and we had a feature map that we generated from our CNN that is smaller, okay, because it usually is smaller unless we use zero padding. And what happens here is that now our 100 by 100 image is now mapped onto a 32 by 32 feature map. Therefore, a window of 20 by 20, that's this kernel size window here, on the original image is mapped to a 6.4 pixel here. This is how a direct linear mapping would be in the feature map. ROI pool, however, rounds down a pixel map to 6 by 6. That is why ROI pool's feature box, when you use ROI pool instead of ROI align, you had misaligned boxes or regions on the image. It may not have been that important when you're looking at a big image with small objects, but if you're thinking about it, if it's a big box that you're going to do a proposal on, being misaligned can actually be bad. So ROI align, however, uses bilinear interpolation to know exactly what would be the pixel at 6.4. So it's a pretty cool, nifty algorithm that gives you an exact mapping without having to round down pixels. So these are some examples of mask RCNN, segmenting and classifying images. It is pretty cool to see this in action, actually. It's very accurate in some videos. Okay, so now let's move on to chapter 20.3, where we talk about single shot detectors, also called SSDs. And these are not solid state drives, by the way. Totally different SSD. So single shot detectors. So we previously just went through the entire RCNN family, and we've seen how successfully they can be applied, alright? However, the performance on video is still not optimal, and they typically run, even on GPUs, at 7 frames per second. Now, SSDs aim to improve this speed by eliminating the need for region proposal. So you can see the speed of faster RCNNs here, and YOLO, and this is YOLO version 1, but look at the speed of SSDs. On relatively high resolution images, they're pretty fast. This is running on a Titan X GPU. So this is pretty impressive. So how did they achieve this improvement in speed? SSDs use multi-scale features and default boxes, as well as dropping the resolution of the images to improve speed. That doesn't sound that difficult, does it? But anyway, this allows SSDs to achieve near real-time speed with almost no drop in accuracy. So SSDs are comprised of two main parts. We have the feature map extractor, and typically they use VGG16. That was actually what was used in the published paper. But ResNet or DenseNet actually could provide better results, as they have actually been better in the ILS VRC result competition. So anyway, then we have the feature map here, and we have the convolutional filter that we use for object detection. So this is a diagram of it here. So basically this is the input image here. This is our feature extractor convolutional network here, which was VGG16. And then we have the convolutional filter that we use for object detectors here, okay? Hi, and welcome to chapter 20.4, where we talk about YOLO, and we go all the way up from YOLO to YOLO version 3. So let's see what YOLO really is about. So YOLO, you only live once, or no, it's actually you only look once. And the idea behind YOLO is that a single neural network is applied to a full image. And this allows YOLO to reason globally about the image when generating predictions. So it's basically a neural net that actually looks at the entire image at first, or CNN. So it is a direct development from or of multibox, but it turns a multibox from a region proposal into an object recognition method by adding a softmax layer in parallel with a box regressor and a box classifier layer. So it divides the image into regions and then predicts bounding boxes and probabilities of each region. YOLO uses a fully convolutional neural network, allowing for input of various image sizes. So that's pretty cool. So more about YOLO. Let me tell you how it works. So the input image is divided into an S by S grid. If the center of an object falls into this grid, that cell is responsible for detecting that object. Now, each grid predicts a number of bounding boxes and confidence scores for those boxes. Confidence here is defined as a probability of an object multiplied by the threshold IIU score, and IIU scores of 0.5 or less than 0.5 are given 0 confidence. So the bounding box is defined by these parameters here, x, y, width, and height, where x and y are the center of the box and w and h are the height and width. By multiplying the conditional class probability and the individual box confidence predictions, we get the class-specific confidence score for each box. That's how YOLO effectively works. So the YOLO model is quite cool. So this is the S by S grid here. These are the bounding boxes that we just generate from each cell, plus the confidence. This is the class probability map. So the class probability map basically indicates, if you go back to it here, the probability of an object being multiplied by threshold score. Okay? And then these are the final detections here. So you can see there's this blue object here, which would belong to that class probability of a dog. Then there was a bicycle, and then there was a background, which ended up being a car. So let's talk about the loss function adjustments. During training, YOLO uses differential weight for confidence predictions from boxes that contain objects and boxes that do not contain objects. It penalizes errors in small and large objects differently by predicting the square root of the bounding box, width, and height. So this is a YOLO architecture. It looks a bit simple, doesn't it? However, it's a lot more going on to YOLO than meets the eye in this image. So let's talk about the evolution of YOLO. YOLO first appeared in 2016. That was the same year faster RCNNs was released, and it was voted OpenCV's People's Choice Award at CVR conference, pattern recognition conference. YOLO version 2 was then later released where batch normalization was added to the CNN. So we do use batch normalization at the end of these layers here, which resulted in map improvements. Remember, map was mean average precision of 2%, which was quite significant. It was also fine-tuned a bit to work at higher resolution images, giving it a 4% now increase in map. And then YOLO 3 was fine-tuned even further and introduced multi-scale training to better help detect smaller objects. So that is it for YOLO, and now we move on to the next section, which is the TensorFlow Object Detection API. Hi, and welcome to chapter 21, where we talk about the TensorFlow Object Detection API. So this section is split up into 3 parts. First part, we deal with the API install and setup. Then we start experimenting with the actual trained APIs. This one is trained on ResNet SSD, and we use it on our webcam and videos and images. And then on 21.3, I go into detail on how you actually would to go about training a TensorFlow object detection model. It's not easy, but it is doable if you have a GPU. Okay, so in 21.1, we deal with the TF-ODI install and setup. So let's talk a bit about TensorFlow's object detection. The TF-ODI API is one of the more mature and relatively easy to use object detection frameworks. Most of them are actually quite finicky and tricky to use. Typically, most other object detection frameworks are finicky, as I just said, and difficult to use, and they break quite easily as they have a lot of moving parts. TensorFlow's object detection attempts to solve that by creating a framework API that uses TensorFlow, no surprise there, to create an object detection modules using both our CNN family as well as the SSD family. So while the TF-ODI API makes it far easier than alternative methods, it still has a bit of a learning curve. By the way, this is actually an output of the TensorFlow object detection API with an SSD. It's quite cool, isn't it? So now let's talk about the install and setup. Now, if you're using the virtual machine with this already installed, you don't have to go through this. However, it's not that hard to do, so I'm just going to go through it step by step. I'm not going to do it with you because I already have it installed on my machine, and I think if I try to reinstall it, I could mess things up. But this is how I did it. Documented everything, and it worked perfectly. So what you do, basically activate your computer vision library. We're not going to install it there because they can have a lot of clashes with packages and libraries being, messy with each other, not mixing well. So let's clone this environment. So we go into terminal and go conda create, and let's call this TF-ODI. We name this environment that. So in future, when you want to activate it, you just go source activate TF-ODI, and it's there. So anyway, copy this line in your terminal and clone your directory, your CV environment, and then run this line here: sudo apt-get install protobuf compiler python py and python lxml and python tk. Okay, then we do pip install Cython, pip install contextlib, Jupyter, matplotlib, and then go back. So we just go back to our main home directory, make a folder called models, and then git clone this basically from here, from this GitHub link here, TensorFlow models, and go back again to the directory and git clone this as well. And now, as we go back here, go into this directory, the Cocoa API, Python API, and enter make. This will compile and build some stuff that you need. And basically just copy this line here, and then these are the comments here, so don't actually run this in your terminal. So this is where we get our TensorFlow models from. So you use wget protobuf zip, and you download this link here, and you unzip this file, and then you can delete this file afterward, it's fine. And then what you do, you get the path that we need to get everything working. So we define this path here, and then we go to our object detection builders, and we run the tests. And if this test runs successfully by opening this file, we will know if this install worked correctly. So go ahead and try it on your own, see if it works. If there's any problems, don't hesitate to contact me. And all the times things change with the, due to updates. So maybe just check this link if this doesn't work first before you contact me. See if there's anything here, maybe a new version or a new dependency, you never know. So running the demo. So download the IPython file in this folder. I actually do have this file in my IPython notebook files there. However, they don't work. You don't run them from that directory. Copy and paste them into this directory here. So let me go to our virtual machine and I'll show you exactly where to find this. Okay, so we're back in our virtual machine, and the directory I want you to go to is, remember I told you based on our presentation here, I wanted you to go to models, research, object detection, and put this file here, or resources file.